Now that we've gone through the process of defining what it means to multiply by an integer, now we're going to go through that almost identical process to define what it means to take an integer exponent. And because we have a little bit of sophistication, I think we can handle all three steps at once this time. So we're going to look at taking integer exponents for a ring R. We're first going to get a recursive definition of positive exponents, very similar to what we did for positive multiples by integers. We're going to define what x to the 0 means, and then we're going to define what negative exponents mean, and then we're finally going to use that to prove a theorem. So let's see if we can define x to the n with n greater than or equal to 1. In other words, n is a natural number recursively, similarly as we did for integer multiples, and we're going to be drawing very heavily upon our intuition about how exponents work. So first, let's let R be a ring, let x be in the ring R, and let n be a natural number. Then we're going to define x to the n as follows. We're going to start at n equals 1. If we have x to the 1, it makes sense for x to the 1 to equal x. Oops, pardon me. The remaining values of n are going to be defined recursively. If n is greater than or equal to 2, then we define x to the n to be x to the n minus 1 times x. And equivalently, if we want to look at it from a slightly different perspective, if n is greater than or equal to 1, then we can define x to the n plus 1 equals x to the n times x. These are identical ways of thinking about exponents. It's just a matter of, do you want to focus on your variable n being on the left side of the equation or on the right side of the equation? There's actually an alternate definition. If you look at the recursive part of the definition, there's a little bit of an asymmetry to it. The x to the n minus 1 is on the left and the x is to the right. There's an equivalent definition where we have the x on the left. So we could define that second part as x to the n equals x times x to the n minus 1. Turns out they're equivalent to the definition that we're given. We can prove that. Maybe, who knows? I might give that to you on a homework assignment. But you can actually prove that by induction. So let's do a couple of examples, or actually we're just going to do one example. Don't get too excited. So if we want to compute x to the third, what is that? Well, by the recursive part of the definition, if we put in n equals 3, we get x to the 2 times x. That x to the 2 is equal to x to the 1 times x, and then that's still times x. And then, of course, we've defined x to the 1 to be x, so we get x times x, and then we multiply that by x. So next we want to look at what happens when we define x to the 0, and I'm guessing you have a good guess about what it's going to be, but let's see if we can find some kind of logical narrative to help us get there. Now, in the end, we expect to have a lot of our exponent laws work for exponents for ring elements. So for instance, we would expect that x to the m plus n to equal x to the m times x to the n, and actually, spoiler alert, that's a theorem that we're actually going to prove a little bit later. But we don't have to justify why we think this is true. It's just if it is going to be true, what does that tell us about x to the 0? Well, if we plug in n equals 0 into that equation, we get x to the m plus 0 equals x to the m times x to the 0. M plus 0 is, of course, equal to m, and so that gives us x to the m equals x to the m times x to the 0. So what does that tell us about what is reasonable to define x to the 0 to be? Well, it looks like x to the 0 acts like a multiplicative identity. At least it does act on a multiplicative identity on powers of x. So it makes sense to define x to the 0 to be the multiplicative identity in R, if that exists, right? Because, warning, if R does not have a multiplicative identity, then defining x to the 0 equal to the multiplicative identity, the one that doesn't exist, that doesn't make any sense. So in that case, x to the 0 is just undefined. Not a big deal. All right, suppose that n is a natural number. What should x to the negative n be? So we're looking at negative exponents here. And I want to look at negative exponents as like having a negative in front of them just so that we can appeal to our intuition. If I just say, let n be a negative number and what's x to the n, that might be a little bit disorienting. So I'm letting n be a positive number. What's x to the negative n? Well, let's see. Let's look at what we would expect x to the negative 1 to the n to be. Now, ordinarily, or back in the old days when we were thinking about exponents, and even in like college algebra courses or high school algebra course, we had an exponent law that told us what happens when we took an exponent to an exponent, and what we ended up doing was multiplying those exponents, right? So we would like to have, if in an ideal world, x to the negative 1 to the n equal to x to the negative 1 times n, right? We just multiply the exponents, and multiplying negative 1 times n, that's just multiplying two integers. We know what that is. That's negative n, so we get x to the negative n. So if we turn that equation around, it makes sense to define x to the negative n as x to the negative 1 to the nth power, right? We know what x to the negative 1 is, right? That should be that's the multiplicative inverse of x, if it exists, right? And then we know what it means to take it to the nth power, because n is a natural number. We know how to do that. Now, of course, we do have to require that x be a unit in order for this to make any sense, because if x is not a unit, it doesn't have a multiplicative inverse, and so x to the negative 1 doesn't even make any sense. That's okay. If x is not a unit, we can just say that x to the negative n is undefined. All right, so let's see if we can put all these definitions together. Let R be a ring, let x be an element of the ring, and let n be any integer. Then we define x to the 1 to be x. If n is greater than or equal to 2, then we define this recursively as x to the n equals x to the n minus 1 times x. If we have n equals 0, x to the 0 is equal to the multiplicative identity in the ring, not the 1 in the integers in the ring, if R has a multiplicative identity. If R does not have a multiplicative identity, x to the 0 is undefined. And finally, if n is less than 0, then x to the n is equal to x to the negative 1, the x inverse, I should say, to the negative n power when R has a multiplicative identity and when x is a unit. And just note that that negative n in the exponent is going to be a positive number because n is a negative number, right? That just like it was back when we were doing negative integer multiples in the previous video. Right, so if n is a negative number, negative n is a positive number. And that means that x to the negative 1 to the negative n has a positive exponent, and we just use the natural number definition of exponents. So, just to let you know, exponent proofs are very similar to the integer multiplication proofs. They come in 3 stages. Our first stage is to prove the theorem for positive exponents. So we use the recursive definition, and because we're using a recursive definition, almost all the time we're going to do a proof by induction. We then prove the theorem when the exponent is 0. And then finally we use the negative exponent definition, and maybe have to use, not just maybe, usually have to use the case of proving it for positive exponents to prove the theorem for negative exponents. All right, so let's try this out on the theorem that I promised you. R is a ring, x is an element of R, m and n are integers. Then we get x to the n plus n equal x to the m times x to the n, right? The exponent law that we always thought we would have. Well, I thought we'd have it anyway. All right, so this proof is going to be a little bit tricky. We have 2 variables that we're working on that are integer variables, and so induction on these things can be really sticky. But we're going to hang in there, and we'll see what we can do. So we're going to prove this using cases. The first case we're going to use is when n is greater than 0, and then the second case is when n is equal to 0. We're going to take care of those 2 cases, and then we'll sort of concentrate on cases for m. And I should note that m can literally be any sign. M can be a positive number, it can be 0, it can be a negative number. We don't care right now. All we care about is n. That is what we were inducting on. That was what we were doing the induction on. All right, so for when n is a positive number, in other words, a natural number, we're going to just proceed by induction on n. And our base case is n equals 1. So we want to prove that x to the m plus 1 is equal to x to the m times x to the 1. However, we know that x to the 1 equals x, and when we replace that x to the 1 with x, we get exactly the recursive definition for exponents when m is a natural number. So that works out just fine. For the inductive step, we're going to assume that x to the m plus n is equal to x to the m times x to the n, and we're going to prove that x to the m plus n plus 1, so we're raising n to the next step, is equal to x to the m times x to the n plus 1. Well, if you look at it, that plus 1 is just really screaming at us that we want to use that recursive definition. Because remember, the recursive definition told us what happened when we had x to a natural number and then we're adding 1. Fortunately, we have the associative property, so we can rewrite that x to the m plus n plus 1 as x to the n plus 1. And now on that right-hand side of the equation, we can apply the recursive definition of exponents to get x to the m plus n plus 1 equal to x to the m plus n times x. And so remember, that was all equal to x to the m plus n plus 1, and so we can set those two things equal. Now, the nice thing about that x to the m plus n is we know a lot about it because of our induction hypothesis. Remember, we're assuming that x to the m plus n is equal to x to the m times x to the n, so we can just sort of substitute it in there. So we get x to the m plus n plus 1 equal to x to the m times x to the n times x. We can now use our associative property on multiplication in R, because remember, ring multiplication is associative. And so we get x to the m times x to the n times x. And if that x to the n times x looks at all familiar, it's because that is the right-hand side of the equation for the recursive definition of exponents. That is literally equal to x to the n plus 1. And so if we replace x to the n times x with x to the n plus 1, we get x to the m plus n plus 1 equal to x to the m times x to the n plus 1. And that is exactly what we were proving. Now, now for the n equals 0 case, that's actually not going to be so bad at all, right? Because if we take x to the m plus 0 is equal to m, so we just get x to the m. If we get x to the m times x to the 0, remember that x to the 0 is just the multiplicative identity. Once again, we get x to the m. Since they're both equal to x to the m, that means they're both equal to each other. So x to the m plus 0 is equal to x to the m times x to the 0, and that's that. Now, we can go through both of those cases again. Instead of doing induction on n, we can do that same induction on m. I'm not going to go through all that pain for you. I'm going to let you do that. Maybe try it yourself. So if we do that, we can prove the theorem is true for m greater than 0 and m equal to 0. Which means, and again, you should try this. I very much encourage you to do that. The steps will be very, very similar. So then we have proved all the cases where at least one of m and n is non-negative. So we proved the case where m is non-negative and n is anything. We have proved the case for n is non-negative and m is anything. The only case left is when they're both negative, right? So m and n are both negative, and so we'll get to work on that case. All right, so m and n are both negative. That means that m plus n is also negative, right? Anytime I add two negative integers together, I get another negative integer. And so now we're going to use the definition of negative exponents on x to the m plus n. So we get x to the m plus n equals x inverse to the negative m plus n. Remember, we know what negative m plus n is. That's just negative m plus negative n. And now we're pretty happy because note that negative m and n are both negative numbers, which means that negative m and negative n are both positive numbers. And we know that our exponent law works when we have positive exponents, right? That's the first case we proved, right? When we took a ring element to the sum of two positive integers. So that tells us that x inverse to the negative m plus negative n is equal to x inverse to the negative m times x inverse to the negative n. And now if those two factors look at all familiar, they are exactly the the negative integer definition of exponents, right? The definition of x to the m when n is negative is x to the negative 1 to the negative m. And the very definition of x to the n is x to the negative 1 times to the negative n. And so we can just substitute those in, and we get x to the m plus 1 equal to x to the m times x to the n. All right, so that takes care of that proof. Hopefully you can apply these principles to the activities. The name of the PDF that is included with this video is called Integer Exponents.